Welcome back. So we're still in chapter 1 of Kuchamann's book, and I was going to work through some of his basic figures on ranges and masses at this wonderful high analytical level. And so remember that he was breaking out the weights in terms of things that scale like the full vehicle. Sorry, this you would think of that as dry mass. There are things that then scale with the payload. So if you're going to go carry more humans or more whatever you're carrying, there's a certain cost to the payload, the weight of the engine, and then the weight of the fuel itself. And then really the form that he then takes in this graph that I'm going to make, and I'm going to have to come back and do some kind of corrections because it's been 50 years. But he then listed, here's C1, here's C2, and then there's a propulsion efficiency times L over D. And remember how the propulsion efficiency goes up with higher Mach number, L over D comes down, and his first kind of catch and look at that, and we'll show it later, is that hey, this is roughly constant. Now, if we're getting better over time, that will go up. So he then defined 3 configurations. He said, hey, this is current state, 1970s. And they said maybe over time with lighter weight materials or different advances, here's the thoughts on B and then C. And so I'm actually going to, in those plots, I'm going to recreate those plots and then actually show you what, say, the 787 looks like. But just for clarity here, that 0.35 was sort of state of the art in the 70s, and then he said, hey, maybe we can get down to where the dry mass, kind of just the structural stuff, wings, fuselage, things like that, would be about 25% of the aircraft. He didn't expect any weight of the engine changes, so this was actually 0.1 in his mind. Now, I'll show you we actually did improve that. And then C2, sort of kind of the what things that scale with payload. And remember, a factor of 1 would be you're only carrying the payload, whether that's I'm only carrying humans or I'm only carrying rubber ducks, whatever it is. And so that factor that was seen in the 70s is 2.5, and he said, well, maybe let's bring that down 2.25 and then 2.0. And so again, that would represent factor of 2 times whatever you're trying to carry. Now, for humans, kind of taking a look, 2.5 is roughly right. In fact, you're going to see that not much has changed much, but I know, especially when you start thinking about going into a really high altitude. So to give you an idea, right now, a person, when people are analyzing aircraft, you would say a person and their luggage, statistically speaking, is 200 pounds. Now, I'm 6'4", and I weigh more than that myself, but they're just, statistically speaking, that's usually what people then use. And then I know from kind of Virgin Galactic Blue Origin days that about 500 pounds per person was roughly what you would expect in terms of all of the things to keep that human alive, the oxygen, all the safety systems, etc. So 2.5 is actually not too bad of a number for even us to think through here at Venus. And then sort of the propulsion efficiency times L over D, that term that sort of seemed to be constant no matter, this fairly constant no matter what Mach number you were treating at. That 3 was sort of what they were using before, and then he said maybe it gets to 4, maybe it gets to 5. Now, this was fun to kind of go dig through. It was not easy to find all of this, but I'll write down here, hey, what's the 787 doing? That's off screen. Apologies. 787. And in the end, the 787 is actually 0.275. So that's kind of the structural weight. That's actually not too bad. C2, now this was interesting, 2.48. Well, so what's happening here, it depends how you count it, but we did reduce a lot of stuff, but then we also added a bunch of things back in. So depending on how you count advanced avionics and APUs, is an APU part of the engine, or is it actually like this is a better way to drive power and starting? So it's a little unclear how you would handle some of these extra things, but best I could kind of do some of the math was roughly 2.48. And then, interesting enough, though, subsonically, this was 8, and that's really interesting because where this is coming from. In the end, the specific fuel consumption of that GEnx engine is 0.53 pounds mass per, that's a pound force hour. Now, I'm a rocket guy at heart, so I usually think about this in terms of ISP, And so ISP is just, the conversion that there was 3,600 seconds per hour divided by that SFC. That gives you the ISP in terms of seconds. Okay, and then this number was at a certain cruise and speed. So just for reference, that was at a Mach 0 of 0.85 and at 37,000 feet. And the important part there is understanding that's not a velocity. Well, the speed of sound A at that altitude is 295 meters per second. Okay, so the reason I say all this is this term that Kuchemann uses, which was H and then A to P, and then of course there was an L over D. This term here, right? In the normal range equation, we wouldn't say H A to P. We would actually say ISP times V, and it's basically an identity. You can show why that's true, and so the ways if I go do this math, has ISP, and I've got the calorific value of the kerosene, the Jet A. And so we end up seeing is that the propulsion efficiency for the 787, which is really the GE9X engine, is about 38%. And then the L over D on the aircraft is pretty impressive. So at that speed, it was roughly at an L over D of 21. So combined, you get the factor of 8. So it was a pretty big leap up in terms of capabilities. So one thing, though, that the Kuchemann analysis didn't do right. So in fact, I'm just going to start showing what does this look like. So you can see here, this was actually the plots then, kind of A, B, and C, the generation. So A was the current generation that he was living. Range here is plotted in terms of circumference. So if you go halfway around the circumference of the Earth, that would be, plenty, right? So maybe you have a mission, you're trying to go all the way around the Earth. Okay, that's a different mission. But 0.5 for our purposes, if you're trying to connect any two city pairs, is plenty. And so kind of looking at what are these terms, what do they do in terms of that range equation we showed last time. Well, there's a plot, and this is payload mass fraction. So it's really, the weight of the payload divided by the weight of the engine. And then I show here what actually happened with the 787. So this is pretty good. And so, as Kuchemann was looking forward into the future saying, hey, maybe there's some advances that would show up. Well, yeah, they did, actually, right? So we can actually fly these aircraft and carry a decent payload of people across the world, all the way across the world. So pretty impressive, really, for people who may not think that aviation has been having tremendous changes. Yeah, it sure did. It sure did. Okay, but the one thing they did wrong in his figure 1.3, he also included hydrogen, because remember for the H value, which I love it in factor of length, it's actually really the heating value of the fuel divided by gravity. But remember, it was 4,400 kilometers for hydrocarbon, and it was 12,000 kilometers for hydrogen. Okay, this is hydrogen. And in this analysis, Kuchemann said who would also plot some hydrogen things, saying, hey, if we could figure out hydrogen, look at that jump in heating value, the useful energy right here. Well, the challenge is that's actually not the correct way to look at it. That part is true, but where he got it wrong was actually this little piece right here, that this is the weight of the fuel, but there's a thing that doesn't scale with anything else. It scales with the weight of the fuel, so let's call that C3. Now, if your fuel, like normal aviation fuel, is actually just a skin tank, that was actually a huge innovation when that happened. It was the same structure that we're using to lift, our wings. Normally, fuel is kind of shoved into the wings. The same structure is basically able to hold our fuel. We just had to make it kind of watertight. So, C3 in our applications is barely over 1. It's not 1, right? It does take a little bit more to hold the fuel in the wings, but it's pretty damn close to 1. So the challenge, though, is this. This is what happens. This is the volumetric density of hydrogen, and the gravimetric density. What you need to see here is how much of the hydrogen in the system, this is a system chart, the system to capture that hydrogen has what kind of volume and what kind of weight. And honestly, the figure of merit, right now, it takes about 11 kilograms of stuff to hold 1 kilogram of hydrogen. right? That's not a good number. And so even showing here that the DOE's target is sort of this 7% gravimetric density, 10% would be 10, right? So it's a pretty big target. And this is from a paper, Now Energy, and also, they were highlighting, well, maybe carbon nanotubes help us get us there. And I actually love this graph. I was looking for a bunch of different ones, but I love this one because it actually showed, hey, there's a way where you can treat all fuels as just hydrogen, and then what's the consequence of carrying that? And so I love that this one actually showed, well, there's gasoline, there's diesel, like, attaching it to a carbon molecule has been pretty helpful. You can find other charts that will show, hey, where does ammonia sit in this? Certainly, we here at Venus, we've played with sodium borohydrate, that's a metal hydride. There are things that we've done here that are familiar to me in this plot. So that's actually the big one that he didn't catch. So if you actually, in this next plot, I then used C as 11 just to be super, like, it's not conservative. It's actually saying, hey, what if we could actually hit this DOE target? And once you do that, you see all these dashed lines would actually represent that system. And so, this is A, this is B, this is C. So once you include that, like the plot you'll see in his book, we're out here saying, hey, man, if we can just tackle hydrogen, we can, smash across the world. The answer is, no, we can't smash across the world, and we can figure out how to hold hydrogen. Now, this is also interesting because there are many aviation companies out there trying to chase hydrogen. And, okay, maybe that's interesting, right? But you're only going to get, 1% the circumference of the Earth, right? And so, this chart, what's half the circumference? The radius of the Earth is, radius of the Earth is about 6,700 kilometers. And so that times pi, basically the circumference of the Earth, what I'm using here is 20,000 kilometers. And so 0.1 would be 2,000 kilometers. So this would make sense. Maybe you're saying, let's convert all short hauls into hydrogen. Maybe there's a world where you're converting short hauls into hydrogen, but it'd be interesting to see how that converts. You're certainly not going to convert any of the long hauls into anything other than hydrocarbons for a very long time. I mean, no one has a graph on how we move this needle even further down. Nobody. Okay, so super interesting to kind of do that one fix on Kuchemann. All right, and then the other part that is not quite fair, and so I've now on the second plot I've added about a 30% drag penalty. This is to incorporate back here. The volumetric efficiency, right, the packing efficiency of hydrogen is not great. Right, you have to catch that this is kind of on a log scale when you look at gasoline and diesel. It packages way better, right? A lot more dense. And so trying to add at least a 30% penalty even shoves that inward. So, it's going to be a little while before we have that kind of system. All right, final plot in that figure 1.3 is this. Now this is interesting. They actually said he said let's try to get some idea. People don't pay for the value proposition is actually something that would say how many people, and let's keep it normalized, and how far are you going? And so this, kind of taking this figure, not the hydrogen ones, taking this figure, and this is the payload, but then multiplying that by range to say, hey, where are the systems, this is some estimate here of profit, of market size, that this is actually what happens. And so you can see here that even as he was projecting forward and saying, hey, maybe we'll have these systems that can really reasonably carry people across the globe. And I think we've seen that, right? We've seen the cost of global travel really kind of come down of you can start building these systems and targeting these different markets. And then I added the conversion there for the 787. Now, this graph doesn't have, and we'll have to come back sort of later chapters as we keep walking through this book. And that's why I kind of love this analysis. Is even looking at this saying, hey, this is an easy way to start understanding what's that market value. What's not incorporated in here is anything related to time, right? I want to go 20,000 kilometers, or I want to go, San Francisco to Tokyo would be 8,000 kilometers, right? So that'd be here. So how do I go do this in a reasonable manner? And so time is going to be then related to the speed that you're flying. And that's kind of the exciting part. So as we kind of dig into this next, you'll see where some of those goes, and kind of, next step, even in this chapter 1, is to kind of Kuchemann goes and starts talking about this a little bit differently. Like, no, this is actually what we're building. This is why we're building these aircraft, and it's a beautiful dive. We'll do that next.